So today, there is a typhoon coming to the Shenzhen, so then we cannot open the Shenzhen venue. So Shenzhen venue only organized only with the online style. So from tomorrow, we will open the Shenzhen venue. So now the first speaker is Hiroaki Kondo. So who is chair? Chair is Professor
Yasumi Yanagida.
Yanagida. So okay, please start, Professor Yanagida. Hi.
Yes, thank you very much. So let us start the first session. The first speaker is Professor Hiroaki Kanno from Nagoya, and he will talk on the PLE formula of supermagnet polynomials. So please start.
Okay. Can you hear me? Okay. Can you hear? Okay. Thank you very much for the introduction, Yanagida-san. So, as one of the organizers and as the first speaker of the workshop, I hope that this workshop gives a good opportunity for the communications among the participants, both on site and online. Okay, let me start my talk. So I'm going to tell you about my recent work with Oka-san and Shiraishi-san. About 3 months ago, we already submitted our first paper to the archive, and there is still work in progress. So if in the last part of my talk, I'm going to tell you our recent progress on the PLE formula of the supermagnet polynomials. So let me start with the ordinary standard magnet polynomials and its PLE formula. So let's consider the ring of symmetric polynomials in xi to xn, n variables. The meaning of symmetric polynomial is that the symmetric group Sn acts on the variable xi to xn, and then the polynomial or the function in this ring is invariant under the action of the symmetric group. Originally, we can define the ring of symmetric polynomial, the coefficient of the ring of symmetric polynomials might be an integer, but we may extend the coefficient to any field to f. For example, we can take f as a field of the rational numbers. The magnet polynomial which we denote p lambda xqt, gives a distinguished basis of lambda f, where we take the coefficient field as a field of rational functions in parameters q and t. And this distinguished basis is labeled by the partitions lambda. And then if the lambda is a partition of natural number n, this magnet polynomial p lambda is a homogeneous polynomial in x of degree n. So, for example, for degree 2, we have two partitions. In my talk, I will describe partitions by standard Young diagrams. And in degree 2, we have two partitions or two Young diagrams, a symmetric one and anti-symmetric one. And the degree of homogeneous 2 polynomial is just a dimension of degree 2 polynomials is just 2, and this is a basis of degree 2 symmetric polynomials. And then the antisymmetric, the magnet polynomial for antisymmetric representation is just a standard elementary symmetric polynomials of degree 2. On the other hand, the symmetric one is more complicated, and there appears such coefficient in the field of rational function in parameters q and t, where here pk denotes the power sum symmetric polynomials. So p sub kx is just a sum of the case power of variable xi. There are two remarks. When the parameter q and t are equal, this Macdonald polynomials reduce to the standard, the more famous sure polynomials S lambda. So note that if we q and t are equal, then both coefficients is reduces to just one. I mean, both in this case, both the coefficient, both the coefficient, denominator of both coefficient just 1 minus q square, and also the numerator is also 1 minus q square. So this coefficient is to just 1. So this is a standard symmetric, sure symmetric polynomials, thus standard character of the symmetric representation and the antisymmetric representation. And another interesting point is these Macdonald polynomials are invariant under the involution of taking the inverse of the two parameters from qt to q inverse to inverse. This is trivial for the second one, but for the first one, if we factor out q times t in both in the numerator and the denominator, we have effectively make this inversion. Note that the denominator flips a sign in this operation, and one of the factor, this and this, also flips a sign. So that the sign cancels between numerator and numerator, denominator and numerator, and this first factor in the denominator is invariant under this operation. Okay, these are two important properties of the Macdonald polynomials. So since the symmetric polynomials are closed under the multiplication, the product of two Macdonald polynomials is expanded in terms of the Macdonald polynomials, since they gives this basis of the symmetric polynomials. So let us consider the special case, the most elementary symmetric polynomials, just the sum of the variables. Just then this multiplication must be expanded in terms of Macdonald polynomials whose degree is 1 higher than the original one. Then since this if lambda is a partition of natural number n, then after the multiplication, this lambda is a partition of n plus 1. So this is it. And this sum is over the partition lambda, which satisfies this sum. This means for each row of the Young diagram, we can put a single box, at most a single box. And then the famous result of the Macdonald is that expansion coefficient is given by this formula, where we put a box in the jth row of the Young diagram. The most simple example is this Pieri formula is the product of two Macdonald polynomials corresponding to the fundamental representation or the box representation. Then this is a degree 2. This should be a degree 2 polynomial. And then actually, since this P box is just a sum of xi's, this is just the square of P1. Then this Q1 square is expanded in terms of degree 2 Macdonald polynomials, and the expansion coefficient is this person. The coefficient of symmetric symmetric representation is just 1. Since in this case, we just put the box in the first row. So in this case, J is just 1, so this is trivial. In the second case, in the second term, we put the box in the second row. Originally, it was empty. Then we choose J equal 1. So we have this factor and specifying this lambda I and lambda J and I, we obtain this coefficient. Then actually, from this explicit formula, we can check this is indeed correct. So the McDonald, PL formula of this is also most basic PL formula for the McDonald polynomials, since we consider the multiplication of P1. Then this coefficient is a result of the McDonald formula. So I'm going to tell you about how this PL formula is generalized to the supersymmetric case. Okay. So let's go to the supersymmetric generalization of the McDonald polynomials. The supersymmetric McDonald polynomials, which I denote carry M sub lambda, generalize the McDonald polynomials to the superspace. By superspace, I mean the superspace has the ordinary bosonic coordinate xi, and in addition to it, we have Grassmann or anti-commuting coordinate theta I. The number of xi and the number of Grassmann coordinate theta I is the same, and the supersymmetric McDonald polynomials are invariant under the simultaneous exchange of commuting and anti-commuting variables. So the symmetric group acts on both the indices of the bosonic coordinate or commuting coordinate xi and anti-commuting coordinate theta I. This means if we expand this supersymmetric polynomials in terms of anti-commuting coordinate theta I, then the coefficient of the expansion is symmetric in some coordinate x and anti-symmetric in the remaining coordinate xi. I mean, the anti-symmetric part is just corresponding this theta I. So the supersymmetric McDonald polynomials is a mixture of the symmetric polynomial and unsymmetric polynomials. As in the case of the McDonald polynomials, the supersymmetric McDonald polynomials are labeled or indexed by the set of superpartitions. So the superpartition is also a generalization of the partition. In the case of partition, the component of the partition is just a non-negative integer. But in the case of superpartition, the component is just takes a also takes a value of the half integer. So a superpartition is a non-increasing sequence of the non-negative element in the or non-negative integer over 2. So we just write in this way. We use a notation capital lambda to distinguish it from the ordinary partition. Then, if this superpartition has length L, the sum of all the components, which I denote by this, is called the level of the partition, superpartition lambda. We can put Z2 grading according to the grading of these half integers. I mean, integral elements are regarded as even, and non-integral elements are regarded as odd. We require that if the component lambda k is odd, I mean, it's half integer, then this inequality is strict. I mean, we assume this condition, which corresponding to the fermionic nature of the superpartition. I mean, if the component of lambda k is odd, we regard it as a fermionic component. Since we cannot have two, since fermions are anti-commuting, that component should only have one. It is convenient to represent superpartition in terms of super Young diagram. It is also a generalization of the Young diagram. So we identify a superpartition with a super Young diagram, which consists of ordinary full boxes and marked boxes by cross. If the component of the superpartition is a non-negative integer, then the end of corresponding row is a full box like this, the second row and the third row. And if the component of a superpartition is half integer, the end of the corresponding row is a marked box with cross. And we count it marked box as 1/2. So the length of each row is just correspond to the component of the superpartitions. So this super Young diagram represents a superpartition lambda 11/2, this first row, and 3, 3, the second and third row, and 3/2 is the fourth row. 1 is just the fifth row, and 1/2 is just the last row. So in this way, we can represent the superpartition in terms of super Young diagram with marked boxes. The row with the marked boxes is regarded as a fermionic row, and the row with no marked boxes are regarded as a bosonic row. And note that for each row and each column, also we can consider the transpose of this super Young diagram. Then for each row and each column, the number of marked boxes is at most 1. So this is also represent the fermionic nature. We also use another expression of superpartition. Capital lambda is represented as a pair of small lambda and sigma. It's a pair of the standard ordinary partition lambda and the Z2 element sigma I. And then the relation of original superpartition is defined by capital lambda I is small lambda I minus 1/2 of sigma I. And if for bosonic case, we take sigma I is just 0, then this is the same as the capital lambda is just a non-negative integer. And for a fermionic component, we take sigma as 1, then this component gives a half integral component. So we use two kinds of description of superpartition, either this super Young diagram or the pair of a partition lambda and sign Z2 elements sigma I. Okay. So here is an example of supermaximum polynomials up to level 2. So it is convenient to use power sum polynomial. So this already appeared. And this second power sum is a fermionic power sum where theta, we there is a theta Grassmann coordinate theta I and times xi to k minus 1. For example, the P1, just P1, when k is 1, this disappears. Then P1 is just sum of Grassmann coordinate, a linear sum of the Grassmann coordinate, theta 1 to theta n. Then we have the supermagnus polynomial of degree 1/2 is just this P1, and Magnal polynomials for ordinary partitions, the supermagnal polynomials are equal to the ordinary standard magnal polynomials. So this is just P1. And for the degree 3/2, we have two superpartitions. One is a 3/2, and the second is 1 and 1/2. So these two are the odd supermagnal polynomials of degree 1 are 3/2. And at level 2, we have three supermagnal polynomials. Two of them are ordinary standard magnal polynomials. The last one is the new one. So this is the product of two Hermionic Hermionic power sum, pi 1 times pi 2. There are two important remarks. That first one is even if we set q equal to t, there still remains one parameter in the case of supersymmetric magnal polynomials. The first non-trivial one is this polynomial. If we put q equal to t, then the denominator is just 1 minus q square, as in the case of lambda m2. But for numerator, it doesn't give 1 minus q square. It's just roughly speaking, it's just a half of the denominator of m2, since this is just a kind of square root of this part. Then there's no cancellation between numerator and the denominator. So there still remains one parameter. So if we define super polynomials as the result of this specialization, this super polynomial still has one parameter. This is a clear difference from the ordinary case. And the second clear difference is the supermagnal polynomials are not invariant under the involution. This is also clear from this explicit formula. Okay, so let's move on the PLE formula of supersymmetric magnal polynomials, and we are going to tell you what is a super Hamiltonian, where the supermagnal polynomials are the eigenfunction of these Hamiltonians. To derive a PLE formula for the supermagnal polynomials, we use the representation theory of the quantum toroidal algebra. In fact, I didn't give you any definition of the supermagnal polynomials, but there are many ways to define the supermagnal polynomials, but one of the ways to define the supersymmetric magnal polynomials to use the representation theory of quantum toroidal algebra based on type GL1/1. This is a kind of super Lie algebra. And then we consider the quantum toroidal version of this GL1/1, which is a quantum group, or more precisely, a quasi-triangular Hopf superalgebra with these generators, EIK, FIK, and K plus minus I plus minus R. And this I takes the value 1 or 2. So this corresponds to GL1/1. So the Cartan of GL1/1 is just two-dimensional. And also, the algebra has a central element, capital C. And these E and F are odd generators. And the algebra has two deformation parameters, Q and T, which corresponding to the two parameters of supermagnet polynomials. And it is convenient to introduce generating currents defined by in this way. This is just sum of the generators with some indeterminate variable x, or spectral, usually called spectral parameters. This is a formal series in Z. Okay. For an irreducible representation is C equals 1, we say it has level 0. And in that case, this Cartan currents are mutually commuting. So this is the important property of level 0 representation. And in this case, we can choose a basis which simultaneously diagonalizes the Cartan generators, K plus minus, or H is just defined in this way. So these generators H are going to be identified as mutually commuting Hamiltonians for the supermagnet polynomials. And some of the commutation relations are maybe this is, we can see the action of the Cartan current, adjoint action of the Cartan current is just gives E. And then there is some degree shift. And this coefficient, there appears this coefficient. And one of the interesting property of GL1/1 algebra is the appearance of this antisymmetric tensor epsilon ij. If this I and j are the same, they are commuting. They are non-commuting. This commutator is non-trivial only when this I and j is different. Since there are only two in this two kinds of indices, 1 and 2, this is enough to keep this relation. And for other odd generators F, that this sign, that overall sign changes. And also since E and F are the odd generators, this means anti-commutator of E and F. And as in the you may be familiar that anti-commutator, or in this case, anti-commutator of E and F gives Cartan part of the algebra. So we are going to use this commutation relation to compute Hamiltonians. And for that purpose, we have to know the action or explicit form of E and F, which we call is a Peery formula for the supermagnetic polynomials. Then we can construct a level 0 representation of the quantum toroidal algebra on the representation space spanned by superpartitions. The action of the odd current EI and FI on the superpartition is described as follows. Note that both E and F are odd generators, so it increases or decreases the degree of the superpartition just 1/2. So both E and F increase the degree just by 1/2, and EF acts on the bosonic law and add marked box. And second one, E2 acts on the Fermionic law, and then E2 replaces Fermionic box to the full box. It also increases the degree just 1/2. And for F, they decreases the degree just by half. In the case of F1, it acts on the fermionic law and delete this fermionic box. And the second F acts on the bosonic law, and it replaces bosonic box to the fermionic box, also decreases the degree by 1/2. So this is a basic representation of the quantum toroidal algebra on the representation space of superpartitions. And we can compute the generating function of the eigenvalues of the Cartan currents. Since we have level 0 representation, as I told you, we can choose the basis which simultaneously diagonalize the Cartan currents. And in the case of this representation, we can take the set of superpartitions as a good basis for the representation. And the Cartan current is nothing but the generating function of the eigenvalues. And this gives the result. Here, I use the convention of describing superpartitions in terms of small lambda and sigma. And one of the important point is, I'm sorry, I didn't tell you it. One of the important point is that k plus minus is just the expansion, is given by the just expansion of this rational function in Z around the infinity or the origin. So k plus is expanded by in terms of the inverse of positive power of the non-negative power of the inverse, and k minus is expanded in terms of the non-negative power of Z. But since there appears these additional terms, we have either 0 or pole at the infinity. So this gives the expansion of k is a rather shifted. Say, I didn't tell you. So here, this anticommutator, here there appears some power of Z according to the behavior of k plus around the infinity. So in this case, the shift appears for plus minus 1. For the first current, K1, the shift is just minus 1. And for the second Cartan current, the shift is just plus 1. I mean, this factor of Z in the denominator gives the shift minus 1. And the shift, the factor of Z, this the single factor of Z gives the shift plus 1. So here is our main conjecture on the PLE rule of supermagnitude polynomials. So the level 0 representation of the quantum toroidal algebra is, the set of superpartitions gives a good basis for the level 0 representation of quantum toroidal algebra. Then we can consider the linear isomorphism, which sends this superpartition to the supermagnitude polynomials. So there is a one-to-one correspondence between superpartition and supermagnitude polynomials. So we can define the linear map. Then the action of quantum toroidal algebra is realized by some linear differential operators on pk and pi k by this linear isomorphism. Then our conjecture is following 4 modes of E and F takes rather a simple form. Then the first one is just the zeromer of the E1 is just a multiplication of pi 1. On the other hand, the plus 1 mode of F1 is just a derivative with respect to the first Fermi power sum. For E2 and F2, it is they are slightly complicated, but still, E2, the zero mode of E2 is a linear combination of the derivative of pi k, and its coefficient is a polynomial in power sum k, pk, and then the generating function of this polynomial ckp is given by this function. And the f2 minus 1 is just a linear combination or the multiplication of pk. And in this case, the coefficient of pk is just a differential operator acting on pk. And again, the generating function of the coefficient, this ck, is given by exponential of this combination. We have checked this conjecture up to level 4. And since this is takes very simple form, we believe this is also true for general level. And also this function is also natural from the viewpoint of the Hamiltonian of Mach-Nernst polynomials, which I will tell you in the next slide. So by using the anti-commutation relation, right here, we can we can express the Hamiltonian. So the most simple Hamiltonian, I mean, this is the first member of mutually commuting Hamiltonians, as the anti-commutation relation of this mode of E and F. Since we have this E2, the form conjecture on the E2 0 and F2 minus 1, we can take anti-commutation relation of these operators to find the expression of the Hamiltonian. For example, so from this anti-commutation relation, we can compute this as a 1 plus, actually minus anti-commutators. Since here's here's minus, so this is actually the anti-commutation relation of this combination. And there are two terms. The first one comes from the anti-commutation of fermionic variables. So this is, since this is it is linear, it is easy to compute anti-commutator of this and this. I'm sorry, here's a typo. This is just k. So this is a diagonal sum of the coefficient. And in the second term, it just comes from the commutator of this p and differential operator of p. And then here there remains bilinear terms in the Grassmann in fermionic power sums, and the coefficient is given by the commutator of this coefficient. Since we know the generating function of this coefficient, we can easily also compute the generating function of this coefficient ckl. Okay. And then the final remark is the bosonic part. This is this part, the second term, is expressed as like this. Since we know the since the generating function of these coefficients given by this one, we just by taking this integral, we just take the constant part of this, which gives just the diagonal part. And this agrees with the old result of Awata, Kubo, Odaki, and Shirai, almost 30 years ago. They give the expression of Hamiltonian for the ordinary Macdonald polynomials, and bosonic part just agrees with their result. On the other hand, for the supermacdonald polynomials, we have fermionic bilinear term, this last term. And, なんだこれは。ちょっとこれはどうすればいいんだろう。I'm sorry. We have the fermionic bilinear term, and this also agrees with the recent proposal by Russian people. Similarly, we can obtain the H1. It has very similar form. I mean, the bosonic part is the same as H2 minus 1. And here is some difference for the fermionic bilinear term. The difference, the sum is not from 1 to but 2. This is the only difference from H1 to H2. And there are also Hamiltonians with plus 1 side. This corresponds to just the inversion of the two parameters Q and T. Actually, the bosonic part of these two are just the inversion of this bosonic part. We take T to T inverse and Q to Q inverse. But there's a clear, very sharp difference in the fermionic part. We observe that there appear higher order terms in fermions. I mean, these two Hamiltonians, the fermionic part is just bilinear in fermions. But for the positive sector, the fermionic part has higher order corrections. So this should be related to the fact that supermacdonald polynomials is not invariant under the inversion of this part. Okay, the time is up. Let me stop here. Thank you.
Thank you very much. So, from Nagoya, is there any question or comment? From Zoom or from net, is there any question or comment? Okay. Then can I ask one?
Yes, please.
So some Hamiltonians appears here, but is there some connection to some physics models?
Physics models. This Hamiltonian. I don't know, but in the case of, I mean, there's some, the reduction to Yang case. So in that model, there is some statistical model of supersymmetric Caruso Sutherland models. In the Yang after the Yang reduction, this Hamiltonian gives the Hamiltonian for such kind of supersymmetric generalization of the integral system. But as far as I know, there's no. I don't know the integral system, a supersymmetric integral system corresponding to this Hamiltonian.
I see.
Okay.
Thank you very much. Then let us restart in 10 o'clock.
Okay. Thank you very much.
Thank you very much.
Okay. Can you hear me? The Zoom? No problem. Oh, okay. So I have to hold the mic like this. This is fine. Okay.
So now let us start the second talk. The second speaker is Shanhan Zhang-san from Nagoya, and he will talk on open n equal to string field theory. So please start.
Okay. So thank you for the introduction, and I'm happy to be here to give this talk on string theory. Okay, so the title is Open equals to string field theory, and it's based on this archive paper. And at first, this is the outline. I will at first spend some time on some brief introduction of n equals to string theory and string field theory. And then I will show explicitly how to build the action for string field theory, and I will end with some outlook. So first, I want to introduce what is n equals to string theory, because this might not be very familiar to most people. So we already know that n equals 1 supersymmetry is a very important part in string theory, like in the conventional NSR string theory and model building. And a natural question to ask is that, can we introduce extended supersymmetry on the string worksheet? The answer is, of course, yes, and this has been done. And then we have strings moving on 1+1 complex dimensional spacetime. So this is a very new object. And because we have now extended supersymmetry on worksheet, this worksheet theory actually carries a lot of symmetry. So apart from the usual diffeomorphism and Weil symmetry and their superpartners S-diff and S-Weil, we now have a new ingredient, the U1 gauge symmetry. And because in the n equals 2 supergravity on the worksheet, there is a U1 gauge field. And thanks to all those symmetries, we can fix the gauge on the worksheet theory like usual. Like we can choose the flat metric at least locally, and we can choose the Gravitini field to be vanishing, and also the U1 gauge field to be vanishing. But the price we have to pay to fix the gauge is we have to introduce the ghost field, just as in conventional Faddeev-Popov procedure in quantum field theory. Here, the B-C ghost system and the beta-gamma ghost system are what we already have for bosonic string and superstrings. Only now we have 2 copies of beta gamma ghost because we have n equals 2 supersymmetry. But here there's a new thing called the B tilde C tilde ghost system, which is introduced to fix the U1 gauge. And after fixing the gauge, we now have n equals 2 superconformal field theory on worksheet. And these are the superconformal algebra. T is the energy tensor, stress energy tensor, and G plus and minus are 2 supercurrent. And we have a new J current, which is the R symmetry current that rotates between the supercurrent. G plus and minus. So with this CFT, we can compute the string amplitude. The standard procedure is just for computing the tree-level amplitude at 0 instanton number. The instant number refers to those of the U1 gauge bundle on the worksheet. And this is the standard procedure. We just insert vertex operators on the worksheet and evaluate the CFT correlator like this. Then we have to sum over all possible copies of Riemann surfaces, which reduces to integration on the modular space. Here there are some new ingredients. First, this is the x plus and minus. They are the picture changing operators from fixing local supersymmetry. So this similar thing already appeared in for superstring, for n equals 1 superstring, but now we only have 2 copies. And we also have B tilde ghost integration around each puncture. This is related to the U1 gauge moduli. So this is special for n equals 2 theory, but not for bosonic or n equals 1 theory. So this is how we compute the string amplitude. And the string amplitude actually defines what we know for a perturbative string theory. The perturbation theory is actually only a set of predefined amplitude as the integrals over modular space, but in contrast to quantum field theory, not from the Feynman expansion of some second quantized action. Here I draw the I think the simplest case of a 4-point function in QFT. You can see that this is a result from a cubic action and its Feynman diagram. So the question of string field theory, or the second quantization of the string theory, is that whether we can build an action, for example, this cubic action, that reproduce the string amplitude here that we already know. So we can we want to write down an action, let's call it S of psi from the amplitude instead of write down the action and derive the amplitudes. So psi here is just denotes a generic string state. So it automatically includes all the tachyons and gauge bosons and gravitons and so on. And people may ask, why do we need to do this? Because we already have all the amplitude and we can compute basically everything, at least perturbatively. And the answer is that we can use the formulation of string field theory for first the analytic solutions that describe the different the changes between different backgrounds, such as tachyon condensation and marginal deformations of the worldsheet CFT. And secondly, there are some problems in string theory that are essentially field theoretical. So they are essentially off-shell, such as mass renormalizations. So it's sometimes useful to have this string field theory action. And right now we have different approaches to write down the string field theory action for different string theories. The first one is Witten's action, which works for n equals 0, the bosonic, and n equals 1 theory, the superstring. It has good the advantage that it has a clear relation to the modular space. So we actually know how this string field theory action derives the string amplitude. And we also have the Bukovitz action, which works for n equals 1 and n equals 2 case. It is good in the sense that it has a compact form, so it's easier to find analytic solutions in this formalism. But but the relation to the modular space and the modular integration is not clear, so we don't actually so it works well, but we don't actually know how it works. The major difference between these two approaches is that the Witten's approach has homotopy algebra. We call it A infinity algebra structure in the action. And this structure has a clear geometric interpretation. So we understand this better. And if we apply this string field theory aspect to open n equals 2 strings, we first notice that the equation of motion of the open n equals 2 strings is the self-dual Yang-Mills equation. So this is already interesting because the self-dual Yang-Mills equations are conjectured to be a unifying principle for a lot of, if not all, integrable systems. And another special unique property of n equals 2 string is that, unlike other string theory, the string oscillation modes, the higher oscillation modes, are blocked. So this string theory is effectively a particle theory. So it's a lot similar to topological string. And actually, these two kind of string theory are somehow related, as shown in this diagram. So on the left-hand side, there are different approaches to integrable systems via quantum field theory, which is already shown to be unified. And for the six-dimensional holomorphic Chern-Simons, it is equivalent to the Witten's approach of string field theory of the topological B model, which is already shown by Witten. And the self-dual Yang-Mills theory is shown to be equivalent to the n equals 2 string theory as Bokowitz's string field theory approach. So we might naturally want to ask the question, can Witten's approach also be applied to the n equals 2 string? So at first, let's briefly review the Witten's approach to string field theory. The simplest case is the open bosonic string field theory, which is like this. And the fundamental component is the Witten's star product. It's a product, so we take two string field and maps to one string field. This diagram shows how to evaluate the product. It's just you put three string fields on the 3 point on the disk and you evaluate the CFT correlator. So using this product, we can write down a cubic action for open bosonic string field theory. And it has a gauge invariance like this, which is a nonlinear extension to the BRST invariance. So this action is gauge invariant. And what's better is that using only this cubic term, the finite amount of terms, we can already covers the entire bosonic modular space. So it's already enough to reproduce all the tree-level amplitudes up to arbitrary points. And going to superstring, we have some subtleties. We have seen before that because we have to now integrate over the supermodular space, and the odd part of the modular integration gives the picture changing operator insertions. And picture changing operators are actually very singular object. So if we, like this, naively, we put the picture changing operators here in the midpoint, then we compute gauge transformation, two PCOs will collide. And since their OPE is singular, so now the gauge invariance breaks. We can resolve this problem by not putting them the picture changing operator on the midpoint, but resolve them by a line integral. But now we have to introduce higher order vertices, and they must obey the A infinity relations to restore the gauge invariance. And for n equals 2 string, let's recall that we now have two picture changing operators, but this can be resolved similarly. Like this, we put them on two line integrals, but still we need a way to determine all the higher order vertices that satisfy the A infinity relation to restore the gauge invariance of this action. So in terms of building the n equals 2 action, we now have a generic action that has a infinity structure. It looks like this. So the omega is non-degenerate pairing, which is built of BBC inner product on CFT, and Mn are multilinear maps. So it takes n string field and maps to one, and we call them M product. So in my work, I showed that if we impose the constraint B tilde zero mode and J zero mode vanishing on the string field, we are able to write down the free action part, the left part of this action like this, and the pairing is defined as this. We insert this C tilde zero mode to saturate the ghost anomaly on the worksheet, so we don't have a vanishing correlator. And now the problem is how to determine the high order terms that stands for the string interactions. In fact, for the n equals 1 case, a systematic way is already available to determine all the high order terms. I will schematically illustrate it very briefly. So basically, this method is to translate the A infinity relation and one extra physical condition into two differential operators. And these differential equations, and these differential equations, when you expand them and compare the coefficients, you get recursive relations between these coefficients. And this recursive relations allows you to determine this product one by one. And you can essentially climb this ladder from the left to the right. And the superscript here denotes the number of picture changing operators insertions. So when you climb it to the right, you get the right number of picture changing insertions. This is how we did it for n equals 1 string. And in my work, I also showed that this can be generalized to two set of picture changing operators, which is kind of straightforward. We just climb the ladder and climb it again. So it's a twofold procedure. And what we conclude is that we now have a full action for interacting open n equals 2 strings. And lastly, I will mention some outlook to this question. So in our construction, we only, as I mentioned before, we only consider the zero instanton sector of the worldsheet U1 bundle. But as has been shown by Bischoff and Leckenfeld in 1996, other instanton number sector is essential to restore the full SO22 symmetry of the self-dual Yang-Mills from the complex U11 symmetry of this string theory. And the second is that how is n equals 2 string field theory related to n equals 1 string field theory of Berkovitz formalism? Because the Berkovitz formalism is based on the embedding of n equals 1 superstring into n equals 2 superstring. So clarifying the n equals 2 modular space will be helpful to understand how Berkovitz string field theory works. And the third one is that recently there has been not very recently, but in 2021 there has been a framework of double copy theory using homotopy algebra. So since the self-dual Yang-Mills theory can be viewed as the most simple example for this, and homotopy algebra is the natural language to describe string field theory. It's interesting to consider this case as the simplest case of a stringy extension of this framework. And that is all my talk. Thank you.
Thank you very much. So from Nagoya, is there any question or comment?
Can you hear? Okay. As you told us that n equal to string theory, sorry, the degrees of freedom of n equal to string theory is highly reduced. So it is something like a particle theory.
Yes.
So I expect the n equal to string field theory is like a standard field theory. Do you agree or disagree?
At least the equation of motion should we can use only the field theory degree of freedom in the equation of motion. So
Can you see that that structure from your result? I mean, in the n equal to case we can. I mean, it is easy to write down string field theory action than the other cases, but at least I can see
yeah,
your slide. I mean, you just use the A infinity structure
yes,
and then determine your interaction term.
yes.
But it doesn't seem to be simplified to standard something like standard field theory.
So you're saying that if there is a way to from the string field theory action and then reduce to the effective field.
Yeah,
theory
I expect the final action is more like standard field theory, since the degrees of freedom is just not string, but just a part.
Yes, actually, this relation is very clear in Berkovitz formalism.
In Berkovitz formalism, it's clear.
Yeah,
in your approach, it is not so clear.
It's not so clear. That's maybe a future direction that we want to clarify, because if you have some I don't know if you have knowledge of Berkovitz formalism, but it's the form of it is very like the WZW formalism, the action, the form. So it's very simple to reduce it to the self-dual Yang-Mills, because self-dual Yang-Mills has the action for self-dual Yang-Mills is also of WZW form. Yeah, so in Berkovitz formalism, these two perspectives are like closely related, but in Witten's approach, it's not very clear.
Okay, thank you very much.
Thank you for your question.
From Nagoya, it's okay. So, and from Zoom, is there any question or comment? Is it okay? Then let us thank San again. Thank you very much.
Perhaps I can share my screen.
Yes, please share, please share.
Yeah, okay, sure. Okay. And then now I should set it as a full screen, I suppose.
Yes, okay.
Okay.
Yeah.
We can see your slide. Yes, then let's start the final talk of this morning session. The speaker is Professor Daniel Wang from Chinese University of Hong Kong, Shenzhen, and he will talk on the entirety of our principal series with presentations. So please start.
Great. So thank you very much for the invitation and the opportunity to talk about some of my recent work and some ongoing work. My talk is going to be kind of introductory. I'm not going to go to a lot of technical details, and rather I will give some background on what kind of things I'm interested in and some of the findings that I and my collaborators have got over the past few years or so. Well, let's begin. So as I said, I want to make things very fundamental. So some of the experts here in the audience will probably know all these things in the very beginning very well. So I will start with quantum mechanics since this is a conference, a workshop on quantum theory. So basically, in quantum mechanics, like around 100 years ago, people started to get some mathematical formulation of quantum mechanics. And in my, from the perspective of a mathematician, I will understand like a quantum mechanical system as a Hilbert space, and then if you want to understand some physical properties of a quantum mechanical system, you will study some self-adjoint or Hermitian operators on this Hilbert space. And since these operators they are self-adjoint, then their eigenvalues are going to be real, and they will give you some measurements of the physical properties that we are interested in the quantum mechanical system. And very simple and fundamental example is the case of the hydrogen atom model. The Hilbert spaces are all these L2 functions in R3. And then you have this so-called time-independent Schrödinger operator, H hat, which is an Hermitian operator on this Hilbert space. And then, you look at the eigenvalues of this Schrödinger operator, and then it will give you the energy levels of the hydrogen atom model. So basically, I will call this H lambda to be the lambda eigenspace of the Schrödinger operator. Okay. So so far so good. And then, what I'm going to do is I want to understand some actions on the Hilbert space given by some groups, which will give you some symmetry of the model that we are interested in quantum mechanics. So so let G be a real reductively group. I'm not going to give a full definition of what a reductively group is, but here are some examples. So basically, many of these matrix Lie groups, and that they are more or less classified by thinking diagrams, and more precisely, they are classified by something called Vogan diagrams or painted thinking diagrams. And so basically, here are some examples of real reductive groups, and then you have SO3, SL2, RUPQ, and then there are also some exceptional Lie groups, which are given by some thinking diagrams of exceptional types, which I haven't listed here, of type G, E, F, and G. Anyway, then when I talk about unitary representation, I'm talking about an operator pi of G acting on this Hilbert space H, so that it preserves the inner product defined by the Hilbert space H. Okay, so let's do an example, very simple example. So in the hydrogen atom model, this L2 space of R cubed. So basically, there is an obvious SO3 action on this Hilbert space. And so basically, all you have to do is, if you apply this G, this element G in SO3 to this function or this on this L2 function, all you have to do is you just multiply G inverse inside, and then this will give you a new L2 function on on this Hilbert space H consisting of L2 functions of R3. Okay, and well, so these are basics, and then well, it turns. I mean, this is if you think more carefully, you're kind of just rotating the space R3 in by this element G in SO3. So basically, well then the inner product is supposed to be preserved because of that, and hence it will give you a unitary representation of SO3 on this Hilbert space H. And well, I mean, if you are going to the Lie algebra of G, then this unitary representation pi of G here in for when G is equal to SO3, it is kind of related to the angular momentum operator of the hydrogen atom model. Okay, and well, and then basically this is how you are understanding some symmetries of the Hilbert space structure of the quantum mechanical system. Okay, so well, moreover, this angular momentum operator, it commutes with the Schrödinger operator, which I just mentioned in the beginning of the talk. So basically, in that case, well, then what we're going to do is well, now we get a very nice understanding of this hydrogen atom model. So basically, to begin with, we can actually divide this. We can actually divide this Hilbert space operator as a kind of completed direct sum of the eigenspace of the Schrödinger operator H lambda i's. And then, as I said earlier, these are lambda 1 up to lambda n. Well, I mean, this is already not something not very obvious. I mean, you get a kind of this direct sum instead of a direct integral. But this is the case for hydrogen atom model. And then this H lambda I, as I said earlier, they are just the eigenspace for the Schrödinger operator. And then you have kind of a distinct energy levels in this case. And since we have this SO3 commuting with the Schrödinger operator H hat, therefore, each H of lambda I is going to be a representation of SO3 as well. And hence, and then, well, turns out that this H lambda I itself, each of these lambda I eigenspace, they are a 2n minus 1 dimensional representation of SO3, and hence you get this very nice picture, which I think many of you are familiar with in quantum mechanics. That you are dividing this hydrogen atom model into a 1 plus 3 plus 5 plus 7 plus 9 and so on dimensional vector space, and each of them they have the same energy level because they are just the lambda I eigenspace on each row of this picture. And then at the same time, on each row, there is this SO3 symmetry on the because we have this SO3 action on each row of the lambda I eigenspace. Okay. So basically, that's the hydrogen atom model, and this is how this kind of representation theory or unitary representation of groups that comes into play in the study of quantum mechanics. Okay, so basically, that's why we are interested in studying the following question. So if I have a real reductive group G, I want to classify all possible unitary representations of this group. And then, I mean, this is a big problem, but at the same time, you can decompose it into some smaller ones. And if I have a unitary representation of G, then you can actually decompose it into a direct sum of irreducible representations of G. Just like what we did before, you can decompose this H into some smaller parts, and then each of them is going to be an irreducible representation. And when I say representation is irreducible, that means if you apply this action of G, then you will get the whole space H itself. So basically, that means the G invariant closed subspaces of H are just 0 and the whole space H and nothing else. Okay, and then well this well, I mean, before I go on, so this kind of question is kind of a problem on Hilbert space. So this is kind of a problem in a functional analysis. And then there is this work by Harishchandra, I think in the 1950s or 1960s, that switches this problem in analysis into the setting of algebra. So how can we do that? Well, so to start with, I have to introduce this K, which is so-called the maximal compact subgroup of G. And then, so for example, if we are working on this group G is equal to UPQ, then this K, this maximal compact subgroup is isomorphic to UP times UQ. Because we know this group of UP and UQ, they are compact, and then they sit inside this UPQ, and it is a maximal compact subgroup of G. And also, for example, if you have this group SOPQ, then maximal compact subgroup is kind of SOP times SOQ, something bigger. But there is a twofold cover of this. But anyway, that's the idea. So you always this you have a compact group lying inside this group G, and then you look at the maximal one. Okay, and then at the same time, I will look at the Lie algebra of this real reductive group G. Okay, and then the work by Harishchandra says that rather than classifying the unitary representation of the group G, well, maybe we can switch it to into this algebraic problem of classifying all unitary unitary representations of GK modules. So of this GK. So basically, I mean, in some sense, since K is compact, then there is some then you well, I mean. So basically, that will switch things into the more like an algebraic setting. You don't have to deal with many issues with integrals anymore. And then you go to the algebra of G. So basically, then we can change the analysis problem into an algebraic problem. So basically, that's the setting. And then, so basically, what we're going to do is we will classify all unitarizable, irreducible representations of this the algebra of G and this compact Lie group K, such that it satisfies some compatibility condition. And I will call this classification problem the unitary dual problem. We want to classify the unitary dual of all these GK modules for a given real reductive group G. Okay, so so as I said before, if we want to classify it as a unitary dual, and then I mean, let me mention some of the progress in this kind of classification problem for real reductive groups. Okay, so in the case when G is itself a compact group, so that means G itself is equal to K. Then we are going back to this very old and very elegant theory of Catan and Val, such that you can classify all its irreducible representations by the so-called highest weight representations. And then in such a case, all these irreducible representations, they have a high unique highest weight. And then it's going to be a finite dimensional. The theories are very nicely built up already in that case. And then there are so-called Val dimension formula that tells you the dimension of each of the irreducible representations for a given highest weight and so on. So this is some theory, once again, back into the 1920s and 30s, nearly 100 years ago, in the case when G is compact. Okay, and then as far as I understand, the first case when G is non-compact is by Bachmann, and I think there are also at the same time some mathematicians in the Soviet Union that gets the same classification on the case when G is GL2R. Okay, so this is a non-compact. This is a non-compact Lie group. So it's obvious why it is non-compact. So if you go to the diagonal, so basically the diagonal can take the values of t and t inverse, or in this case, it can get any non-zero value a and b on the diagonal. So it's obvious that well, this cannot be closed and bounded. Okay, so GL2R, well, there is also a full classification of the unitary dual in the 1940s, and then somehow it takes a long time to get some classification for a non-compact group G. For example, the case of GLNR is done by Vaughan in 1986. So it's already 40 years after the classification of GL2R. So basically, this is kind of like a slow progress in some sense. And then it is still ongoing. So the full classification is not known yet for any given group G. So basically, that is the kind of work I'm interested in to give full classification of the of any given group G. Okay. So anyway, so you can see some of the work. So basically, also there are some covers of some of these linear groups that we want to classify as unitary dual. One of them is given by Jin Sung Hwan, which is some double cover of GL and R, and then in Vaughan. As I said earlier, we want to understand the unitary dual of exceptional Lie groups as well. And then this in 1994, Vaughan gives the classification of the universal cover of this Lie group of type G2. Then recently, I think well, just a few years ago, so myself and my postdoc, Hongfeng Zhang, we have some classification for the group UN2 and also the group spin NC. Okay, and I will show you some pictures on on how this unitary dual is like for UN2 in a moment. Okay. So basically, this is still an ongoing, long process. I mean, this has been 100 years, and the unitary dual is not classified yet. Okay. So well, let me mention one of the big progress that we have in the classification problem of the unitary dual. So I think that goes back in the 1990s. So a group of mathematicians. They have built up a computer program which we call the Atlas program. That first of all, the first thing that they did is they list out all the possible candidates for of irreducible representations or irreducible GK modules. And then the second thing that they did was, among the list of irreducible GK modules that they have listed, they want to determine which of them are unitary. Okay, and so basically, in I think in in 2007, they have succeeded in listing all these irreducible GK modules for the split real group of exceptional type E8. And then at that time there was a lot of attention by the media, and then well, so this is only of course this is a milestone for their progress, but they do not end in there. They have successfully listed all these irreducible representations. They have listed the possible candidates of representations that are unitary. And then for the next 10 years or so, they work on the problem of determining which of them are unitary. Okay. So finally, in 2016, they have developed this code in Atlas program is unitary. So that for the candidates of irreducible GK modules that they have listed, they can determine which of them is unitary and which of them is not. So good. So basically now that means what? That means now we have a computer program. If you feed in one irreducible representation, it will tell you whether it is unitary or not. I mean, this is nice, but at the same time, it doesn't give you the full classification problem. So I think this is a very good analogy. So Of course, if you have some very basic knowledge on programming, you know how to write a program, let's say in Python, to check whether an integer is prime or not. Okay, but so now you have so that means what? That means if you feed in an integer n, then this program will tell you whether this integer is a prime or number or not. But does it give you the structure of the distribution of prime numbers? For example, can you prove this so-called what I think prime number theorem about the growth of prime numbers as n increases? It doesn't. Well, it's nice that you can find a way to check whether an integer is prime or not, but it doesn't give you the whole picture of the distribution of prime numbers. Okay, and the same thing holds for this program is unitary. It tells you a particular representation is unitary or not, but it doesn't tell you like the full picture of the unitary dual. I mean, in some sense, for example, if I fix a group G, let's say exceptional group G2, okay, then of course this is unitary. I mean, there is a lot of infinite issues that you have to work with. I mean, there are infinitely many candidates, and then you can and only finitely many of them will give you a it turns out that essentially only finitely many of them will tell you the structure of the unitary dual of G. So basically, that's the thing that we have to deal with. I mean, you have a program to check whether a representation is unitary or not. It will give you some evidence or some insight on how the structure of the unitary dual is like, but it doesn't give you how exactly it is in general. Okay, and that's some work that we have to work on. Okay, so now let me focus on the case when G is so-called a split reductive group. In the case, so I have listed some examples. ONN plus 1, SP2NR. They are so-called a split reductive group. So if you are familiar with Lie theory, whenever I talk about a reductive group, there is this notion of a rank of this reductive group, which corresponds to the number of nodes in the which is roughly corresponding to the number of nodes of the thinking diagram it corresponds to. And then at the same time, in this group G, I would like to look at the kind of this maximal abelian subgroup of G. And then it turns out that, when I talk about split, that means this one possible maximal abelian subgroup of G has to contain these copy of R star, where, and then the number of copies of R star in G has to be equal to the rank of G. So this is what I mean by split. But in any case, so this is a very important class of reductive group. And then, in the case, this K is a maximal complex subgroup of G. And then for the G that I have listed above, I have also listed what the Ks are. And then, what we are interested in, rather than looking at the full unitary dual of G, I will look at the small part of it, but it's also a very important part of the unitary dual. I will call this the spherical unitary dual. So I'm looking at the unitary representations of G. In other words, I'm looking at the representations of GK of GK, where G is the Lie algebra of G and K is the maximal complex group of G. And then I'm just looking at the representations that has a K fixed factor. Okay, so that basically that means there must be a factor in this representation such that if you apply this K action on it, it stays wherever it is. Okay, and this is called the spherical unitary dual of G. Okay, and then so this is kind of like a small part because not all representations of G will have a K fixed factor. But it is a very important part in the classification problem of the full unitary dual. So I think this is a very important first step to understand in order to get the full classification. Okay. So so in such a case, then we want to classify all possible unitary representations of G that has a k-fixed vector. And it turns out that, well, all these candidates of representations with k-fixed vector, they are parameterized by a factor nu in Rn. Okay, and as I said earlier, this n is precisely the rank of G. Okay, and well, I mean, with some, well, I mean, roughly, I mean, there are some kind of Boolean group that we have to play with, but roughly speaking, it is just the rank of G. And then in this case, well, so the question is, if I have a factor in Rn, then there is a so-called this Langland's quotient J of nu. And this J of nu is it's going to be a spherical representation. It's going to have a k-fixed factor, and it is irreducible. The question is whether this J of nu whether this J of nu is a unitary representation or not. Okay, and well, it turns out that well, for all such split groups, this spherical unitary dual is known precisely. Okay, so let me just give you some pictures on the case when G is O32 and the case when this G is the split exceptional group of type G2. Okay, so as you can see, as I said earlier, all these groups they have rank 2. And that means, well, I mean, that means all these spherical quotient J nu, they are parameterized by factor in R2. And then it turns out that only these, I mean, only these shaded square in the case of O32 with some kind of with some isolated dots. These values of nu will give you a unitary representation, and the others are not. Okay, and in the case of G2R, okay, in the case of exceptional group G2, well, once again you have this very interesting shape. So basically, you have this hexagon inside. All these points inside the hexagon, the nu corresponding to it will give you a unitary representation. And then, well, these isolated dots, they are actually the trivial representation. There is obviously obviously one-dimensional representation Gx on this one-dimensional space trivially, and these are the isolated dots. Okay, so as I said, I will show you some pictures on UN2 as well. So there is also this picture, spherical unitary dual of UN2. So so basically, in the case of UN2, this picture, I think this is the picture of U92. So as you can see, I'm in the case of U92. As I said earlier, the maximal compassive group is U9 times U2. And I want there is this k-fixed factor in my unitary representation, and then the picture looks like this. Okay, so I'm just only showing you the first quadrant. So basically, if you are if you're kind of reflecting this picture to the second, third, and fourth quadrant, you'll get the full unitary dual. Okay, so so basically, this is the kind of picture that I'm interested in. What kind of nu will give you a spherical unitary dual? And in the case of U92, we have the answer for that. Okay, so anyway, so let me go back to my slides. Okay, so so this is already known. I mean, and in particular, Atlas, the program, can actually give you this picture. But once again, you give Atlas, you fix a group. Let's say in this case G2, then it will give you this picture. You fix the group O32, then this program will give you this picture. But the problem is this. I mean, if I'm giving you a random OPQ, P can go to infinity, Q can go to infinity. Okay, then you cannot ask Atlas to list infinitely many P and Qs for these pictures. you want to get a unified description of the unitary dual for OPQ, okay, or UPQ, and that's the thing that we have to work on, okay. But in any case, I'm going to do something slightly different. So on the last slide, I'm interested in the case when my representation has a k fixed factor, okay? And in this case, I'm generalizing my situation a bit. Rather than requiring my representation as a k fixed factor, I want the representation contains a so-called fine k representation. So, for example, in the case of ONN, I want my representation to contain this k representation, which PC to the n times c, and then and these are the other cases for the other groups, and in particular, in the case when p is 0 in these cases, then then you get wedge 0 of something. Then this wedge 0 of something is of course just C itself, and then that means this lambda delta n is just a trivial representation. Okay, and then that means in the case when p is 0 and q is n, then we are back to the case of the previous slide that we are classifying the spherical unitary dual. Okay, so we're generalizing this from delta 0 n to delta pq when we are studying representations that contains a fine k type. Okay. And then, well, once again, you want to ask this question. So when is this representation unitary? So once again, for all these representations containing a fine k type, they are parameterized by a factor in Rp and a factor in Rq. Okay, and then once again, you want to ask the same question for what values of this factor nu p in Rp and and nu q in Rq, when is it unitary? Okay, so there are some partial results for that. Okay, so it turns out that the answer to this question, or a partial answer to this question, is something related to something called the endoscopic subgroup of G. But I'm not going to define what that is. I'm just telling you what they are. Okay. So well, in the case when G is ONN, then G1, G2 is going to be OPP and OQQ. Okay, and then if G is ONN plus 1, then G1, G2 is OPP plus 1, OQQ plus 1, and then and so on. And then, well, it turns out that, so this is work by Babash, Shibutaro, and Pantano, I think in the late or middle to late 2000s, so some 15 years ago or more. So they have given a partial answer to this question. They are saying that if this representation if this representation containing a fine k type is unitary, then you just look at the nu p part and the nu q part. Okay, then this nu p has to be in the spherical unitary dual of this group G1 that I listed, and this nu q, J nu q has to be in the spherical unitary dual of this group G2. Okay, so so basically that means we have kind of a bond on how or when this representation containing a fine k type is unitary, because we have already known this spherical unitary dual of G1, and we already know the spherical unitary dual of G2 according to the last slide. So we get a bond. So that means this unitary dual with a fine k type delta pq has to be bounded by this spherical unitary dual of G1 times the spherical unitary dual of G2. Okay, so so basically then there is a conjecture. I mean, you don't just want a bond; you want it to be exactly equal. So so basically, this is a conjecture by Babash and Chibutaru, and then by Pantano, Paul, and Salamanca. So they are saying that you don't only get a bond on these on this fine unitary dual. They are exactly equal to the unitary dual of G1, spherical unitary dual of G1 times the spherical unitary dual of G2. Okay, and then this is still some work in progress. So I'm working on this with Lin Li in Nankai University. So this conjecture should be true in the case when G is equal to ONN plus 1. And we are expecting this to hold for other classical Lie groups that we have mentioned as well. To end this talk, I think I will just give you a picture on how this is like. So, on the left-hand side, you have this. We already have this picture of this spherical unitary dual of O32 on the previous slides. Okay, and then the spherical unitary dual of O21 is actually very simple. Somehow it's just the unitary dual of SL2R after some scaling. So basically, in this case, the spherical unitary dual of O21 is just this interval minus 1/2 and 1/2. And then, we have already this picture of spherical unitary dual of O32. Then, the answer to this, so basically, then you want to look at the unitary dual of this representation with the fine K-type delta 2, 1, and in O43. And then, all you are doing is you are just taking the Cartesian product of these two unitary duals, and then you will get this unitary dual of O43 in such a case. So of course, in such a small case, I mean, you can do this by Atlas. So Atlas can tell you that this is precisely the unitary dual. That is fine. And also, even back in the days without Atlas, I think in this small case of O43, these authors, Pantano, Paul, and Salamanca, they have already proved that this is indeed the unitary dual with this fine K-type delta 2, 1 in O43. But the question is, once again, you have to deal with this problem of infinity. I mean, can you generalize it to all from O43 to O54, O65, and for ONN plus 1? And then this is the thing that we have to work on. And and then it turns out that this is indeed the case for ONN plus 1. As I said, we will expect this to hold as well for these other groups that I have listed on the previous slide. Okay. So I think this is a good place for me to end the talk. So thank you very much for your attention.
Thank you very much. And so, is there any question or comment from Nagoya? So,
Sorry, I have a question. So, okay.
excuse me, one question
From Nagoya side.
May I ask a question about, in your picture on the unitary dual of O32, I don't quite see the meaning of that picture. There is a black square on the origin, and there are, I think, eight spots.
Okay.
8 spots. What's the difference or what's the meaning of this picture?
Let me go back to this picture here. Yeah. This is not the full picture of the unitary dual. It is only a small part of the unitary dual, but it is a very important part of the unitary dual. I'm only looking at representations that has so-called a K-fixed factor. Basically, in such a case, all these representations, all these irreducible representations with a K-fixed factor, they can be parameterized by a factor nu in Rn. So in the case of O32, all
it's n equal 2, right?
Yeah, that is right. Yes.
It represents on the plane. Yes.
Yeah, that's right. Yes.
And there is, the square, black square and black spot. Are they different or?
Yeah, they are different. Let's see if I can. I'm not good at writing here, but but I think I can type. So basically the black. So let me get this smaller. So the black square here. So basically, they are sometimes called the complementary series. And then they are sometimes
so it has continuous parameter.
Yes, it has continuous parameter. Yes, and then basically so basically this is something like this, okay? And then this new is precisely well running inside this square. And then this is the so-called so in this case J new is equal to this, okay?
And
then
one?
Yes, the isolated dot is J. In this case, it is 3 half and 1 half, and then it is just a trivial representation. This itself is C itself. It's a one-dimensional representation, and then well, pi g acting on this. I mean, pi g acting on this. Let's say span of V is always equal to V itself.
I see. So these are qualitatively different.
Yes, very different. I mean, this complementary series representation is a very big infinite dimensional representation. But this isolated dot here, and actually the same goes for this picture of G2. It's also these isolated dot, they are trivial representation. It's a finite dimensional, or more precisely, one-dimensional representation. Yeah.
And in the last slide, you also present the unity ideal of all four three-dimensional picture.
Yes. Yes, here.
Is it the same? I mean, you have some big cube in the middle, and the line. Straight line. The explanation or the meaning of these are also the same, similar to the O32 case?
Kind of, but not exactly. So once again, here, well, what is different is on the previous picture, I have a factor that that is fixed by the maximal compact subgroup of K. So this picture on the right-hand side, you don't have this factor anymore. But in any case, this is a big box. It is still called a complementary series. And then in this case, this J, well, I will just call this new P, new Q. It is still some induce from B to G. And then, well, I mean, before you only have this E to the new, but here you get something like, I don't know, some kind of a sign character times this, but roughly the same, okay? But this is there is a slight difference here.
Okay, thank you very much.
Yeah.
Thanks
for the question. Yeah.
Thank you. How about on the Zoom?
Okay, I have a question. Okay. Hello.
Yes.
So I'm quite confused. So because you consider quite a general case, but I believe that this one include the case of SU11 or SP2R symbolic group. So in that case, SU11 case, there is a three kind of representation: discrete series and principal series and complementary series. So how to characterize it? But you didn't explain that kind of discrete case and continuous case. So I'm very confused.
Yeah, I totally understand your question. So let me go back to this picture once again. So as I said earlier, what I'm doing here is so-called let's see if I don't want to type too much here. But what I have been doing in this picture here, I'm not classifying the full unitary dual. What you are describing is the full unitary dual of U11 or SP2R. And what you said is completely correct. There is a discrete part and there is this continuous part. And in some sense, I'm not describing the full unitary dual of sp2r or u11 in this picture. I'm only describing something called the spherical unitary dual. And then in that particular case of u11 or sp2r that you just mentioned, the spherical unitary dual is only the complementary series part that you mentioned. And then so I think I will try to do it here. So the discrete part of a unitary dual of U11 or sp2r are not spherical. So for example, in the case of in the case of U11, you will get a kind of representation in the discrete part, and then they do not have this k-fixed factor anymore. It turns out that this fact, they don't have a k-fixed factor. They don't have this fine k type that I mentioned in the next slide as well. So they are kind of like on the other side, or they are totally outside of scope from mine. So the discrete part, the way that I'm understanding the discrete part of what you mentioned, I mean, it can be kind of understood from the well, I mean, what? Yeah, how should I put this? So I mean, well, anyway, the quick answer is this spherical unitary dual does not include. It's not the full unitary dual, so it does not contain the discrete dots that you mentioned. But these discrete dots, there is another way that I can handle them, and I can construct them, which I will call them cohomological induction. So basically, I will treat them in a different way in the classification problem for the discrete dot. So in this case, I don't have all these discrete dots that you mentioned because they do not have a k-fixed factor. Yeah.
The condition of k-fixed vector is crucial.
Yes.
So I could not understand how did you define the k-fixed vector? K is the maximal compact group.
Yes.
Maximal compact group, that vector is not change the application of the maximal compact group. So this is
That is right.
definition of the spherical unitary group, spherical unitary dual.
Yeah.
Okay.
Yes. Yes. So
So
for example,
discrete case doesn't satisfy. Okay.
that is right. So and then you can see this isolated dot case that I mentioned earlier. So this factor V is not only k fixed, it is g fixed in some sense, and that is why it is of course k fixed. Yeah. But the discrete dots that you mentioned in U11 and sp2r, they do not have this k fixed factor.
But in the case of SE11, there is an eigenstate. That's kind of eigenstate of that's U1 subgroup, I think. U1 subgroup stabilizes some specific states. So this one definition of the discrete series.
I mean, so for example, in U11, I think the discrete dots that you have that you mentioned, so it's a U11 representation. So there is this U1 times U1 action. So K in this case is U1 times U1. And then, the representations of U1 times U1 can be represented by Z times Z, integer times two integers. And then in your discrete case, the difference between these two integers are going to be greater than or equal to 2. So, I mean, in some sense, I mean, but if you think more carefully about the complementary series, then it has a k-fixed factor.
Maximum countdown is not U1.
Just
U1 times U1.
yeah. So
Maximum
SU.
compound.
No. Well, if you say SU11 is kind of S bracket U1 times U1.
U1 times U1.
Yes, and then so they are represented by two integers. And then since
Okay, I understand. But no, SU11, I want to consider the case of SU11.
right, that's right. So in this case,
SU11 case only the one dimension maximal compact subgroup SU11.
yeah, that is right. Yes.
So in that case, in the discrete series, that's U1 subgroup stabilize the one element, that vector. So this is same as a spherical unitary, I think.
Well, I think I will go to another place. Your case of SU11. Okay, so I think I will write in this way. So if G is SU11,
Yes, in
K
that case,
is U1 times U1. Okay.
hmm?
And then,
Hmm.
so basically, the reps of
SU1, U1. Essentially, this is U1, I think.
yeah, I think this is it. By two integers, a, b, with well, I mean, I think a well, actually, give my a minus a. For a in z. Okay. And then the discrete part that you mentioned, the discrete series, this a has to be greater than or equal to 1.
Well, anyway, this is integer, so a must be integer. So then this is discrete.
Yeah, maybe I don't know. Maybe you can get something like 1/2 of z. So yeah, 1/2 of z. Yeah,
Some discrete value.
Yeah, definitely. And then the discrete series is the case when a is and then when I talk about spherical, I'm talking about the case when a is 0.
But I'm very confused. What is a fixed vector? Fixed vector means that a must be 0.
Yeah, that's right. In the discrete series case, your a is greater than or equal to 1 all the time.
You assume that phase factor also must be 0. Phase factor must be 1.
That is right. Yeah.
Phase factor must be 1. Okay. I understand. So this is slightly different. So
yeah, that is right. Yeah. But in the case of complementary series, a is 0. Yeah.
Okay, I understand. Okay, so phase factor also need to be vanished. Okay, I understand.
Yeah. And then yeah, I don't want to write too much, but when I say fine, is a Ka is 0 or 1/2. Fine.
Okay, I understand. So phase factor must be vanished. So
yes.
Is it okay? Yeah.
I understand that point.
Yeah.
Well, time is up, and so let us thank Wan-san again, Professor Wan.
Thank you very much.
And the morning session is over. We start at in Japan time 2:30 and China time 1:30 p.m. Yeah, see you again.